In today's lecture, we will talk about the duality property of the CTFT. I will start by explaining the concept of duality and then talk about some applications to some properties of the CTFT related to frequency shift and derivation and integration of frequency, and then I will end up with an example on bandpass filter. There is a kind of duality or symmetry between CTFT pairs. Let's first explain it through an example. If you remember, we first focused, or one of the first example we gave at the beginning of this lecture is to understand how does the impulse response of a low-pass filter here looks like in the time domain. So this is here low-pass filter that let only frequencies between -W and +W go through the system and filters out all the high frequencies. And if you remember, in the time domain, when we did the inverse transform, we get the sinc function. So it looks like something like this. So this is the sinc function here, which is this one here. So its sign actually here, it should be omega t. So I will fix it in the slides. So a sinc function in the time domain gives you a box function in the frequency domain. And duality says that if you flip the time and frequency variable, you will get specifically or kind of the same transform, meaning that if you look at a box in the time domain now, you will get something similar to a sinc function in the frequency domain, and this is what we're talking about here. Now notice it's not exactly the same, because here the sinc function you have a factor pi, and here you don't have pi and you have factor 2, but it's kind of the same. Now the reason why, and you'll see why this happens, is because of the CTFT transform and the inverse CTFT transform. They're basically the same. So if you have a signal x of t, then x of j omega is the integral between -infinity and +infinity of x of t e minus j omega t dt, right? And now the inverse transform is kind of the same, except for that there is a factor 1 over 2 pi, and this is why you have this kind of little discrepancy here. The integral of x of j omega e j omega t d omega. So again, and there's this, the second difference is that here instead of minus omega, here there's plus omega. So which means that if the signal is not symmetric, you'll see a flip. But in general, so this says that there's this duality that exists, meaning for every pair in the of transform between time, a transform from the time domain to the frequency domain, if you flip the variables, you'll have a very similar frequency and even a similar property. So again, duality says that what we just saw with the example of a LPF filter, where a sinc in the time domain transformed to a box in the frequency domain, and the box in the time domain transformed to something very similar to a sinc function in the frequency domain. This is not a particular specific example that works for this function. It's a phenomenon that we observe a lot, or can be observed a lot when looking at these transforms. And again, it follows immediately from the expression of the CTFT and its inverse. They're almost the same except for a few changes. So for every transform pair, there is a dual pair with the frequency and the time variable are interchanged. And also for every property, such as the time shift, which we know from previous lectures that a time shift by t0 is a multiplication by e minus j omega t0 in the frequency domain. There is something equivalent in the frequency domain. And the equivalent property in the frequency domain is the following here for this specific example. So if I want to shift the Fourier transform of a signal by a certain amount, and we'll see later that in many applications we will have to do this, then all I have to do is to multiply by ej omega 0 t, the signal, basically multiply it by cosine and sine. So multiplying by ej omega 0 t results in shifting the spectrum of the signal by an amount equal to omega 0. Now the proof, you can see it here, but for me what's interesting is to see this property as a dual of the property related to the shift in time. So the shift in time is a multiplication by an exponential in the frequency domain, and also a shift in the frequency domain is equivalent to a multiplication by an exponential in the time domain. Also, you can derive properties related to or that are equivalent or that are dual of other properties that exist that we've seen before. For example, we've done before derivative in the time domain and integral in the time domain, and here we have two relationships that are, and properties that are related to the derivative in the frequency domain, which essentially is multiplying by minus jt in the time domain, and a property on the derivation or integration in the frequency domain, which is essentially a division by jt, or by a negative jt plus the constant here. As an example of duality, let's take the following example of how to transform or how to get the impulse response of a bandpass filter from a low-pass filter. So if you, just to remind you that a bandpass filter, it looks something like here in the frequency domain. So it's a box in the interval minus b and plus b. And the bandpass filter, we kind of want to only let certain frequency pass. So it probably looks something like this. So this is low pass filter, and the bandpass filter, I mean, suppose you want, given these frequency to go through, let's say. Now you can see that, so this is the bandpass filter. Now the question is how to construct this bandpass filter. If you look at it for a second, you can see that the bandpass filter is a shifted version of the spectrum of the low-pass filter. So it's a frequency shift. So we can just apply the frequency shift property. Again, here the bandpass filter is a sinc function in the time domain, and I have to do a frequency shift, which means that I have to multiply by ej omega 0 t here. And this is what I was mentioning, which is that the bandpass filter here, so this is the bandpass filter, is a shifted version of the low-pass filter. And here I would tell you that you need to design a bandpass filter centered around omega 0 and the LETs frequencies in the interval omega 0 minus b and omega 0 plus b pass. Again, so in the time domain, you know that the shift with omega 0 is multiplication by ej omega 0 in the time domain. So a shift in the frequency domain is a multiplication by ej omega 0 t in the time domain. Now this would be the solution if you want, but in practice we would like the signal to be real, so what we have to do is to add the imaginary component by basically adding the conjugate here and dividing by and multiplying by 2. So, and adding the conjugate here would be adding e minus j omega 0 t sine bt by pi t, in case you want to make it a real. And this is gonna get rid of the imaginary part. And probably you have to multiply by 2 if you want to keep it 1, because here you're gonna get 2 times something. So this is basically what I'm doing. I'm adding, this is the signal, and I'm adding the conjugate of it, which is another shift by minus omega 0. So in the frequency domain, I get these 2 parts. If you remember the properties of the real signal, that it is conjugate symmetric, and this is what's happening here. So I'm making it symmetric. Now by doing so, you get the impulse response of the band pass filter, which is equal to 2 sine bt divided by pi t cosine omega 0 t. So basically multiplying, so the takeaway message here is that multiplying by cosine omega 0 t, this is gonna make the filter a bandpass filter. It's gonna take it from being a low pass filter to a bandpass filter centered around omega 0, which is here, and the interval is of length 2b. So it's gonna be b and b. So this is omega 0 minus b and omega 0 plus b. So this is how the filter is gonna look like. And in many applications, we would like to, if another example where we would like to do this is when we're transmitting a signal over an antenna, for example. So the signal, the frequency in the signal would be limited. Let's suppose it's your voice or it's some music. But to be able to transmit over the antenna, the frequency has to be very high. I mean, for example, certain wireless communication, the frequencies, you can look it up, which frequencies are 2G or 3G or 4G or 5G. What are the band? Let's suppose maybe in 3G it's 900 megahertz. I'm not sure about these numbers, but you need to shift your signal to that frequency to be able to transmit it, and this is how would you shift it. So I gave the example of wireless communications that you use on your cell phone, but maybe another application that's now not widely used, but maybe it's good to teach. An example is the AM radio. So typically nowadays, if you listen to the radio, it's going to be more FM radio frequency modulation. And you'll take these in another class. But for amplitude modulating radio is the baseband, the signal whose spectrum lies between minus B and plus B. So here the keyword is a baseband signal. So if you take the digital communication, you're going to go over this in more details. So the baseband is the signal you're going to try to send, which is, let's think of it, maybe the audio of an interview or the singing or music. And the spectrum lies between minus B and plus B. Here the spectrum is going to tell you how good the quality of your music is. Now, as is, you cannot transmit the signal because it has very low frequency. So what you need to do, you need to modulate it by multiplying by a cosine to shift it to a high frequency that you can transmit. And this is called amplitude modulation, or AM. And this high frequency is the carrier frequency, which is centered around omega 0. So all you have to do is multiply by cosine omega 0 here. Again, if you're interested in this topic, you can you can learn more about it in digital communication classes, or you can read more about it online. So my goal here is just to give a quick example on the applications of this property. The main thing to keep in mind here is that a multiplication, a shift in the frequency domain, you can achieve this by multiplying by ej omega 0 t, and if you want to make the signal real, you just multiply, you have to multiply by cosine omega 0 t, and then you're going to shift everything to be centered around omega 0 t. And this has many engineering applications. Continuing with the AM or amplitude modulation example, so typically you're going to have, your signal is x of t, which is here. You're going to have to multiply it by cosine omega 0 t, like we said, because you need to be able to modulate it to be able to transmit it on an antenna, so omega 0 is the carrier signal. Then the transmitted signal is going to look something like this. Its y of t is A, which is gain from the amplifier. One is called the DC offset, and K is the signal gain. And now you can, so the transmitted signal looks something like this. And you can analyze the spectrum of yj omega using xj omega and the CTFT property. So usually what you receive here, you're going to receive this plus some noise. On the other hand, at the receiver side, maybe with some fading here, meaning the amplitude, the energy of the signal is going to decay depending on the distance. And then your goal as a receiver is to recover x of t here. Again, you'll see these in more details in other classes. As a take-home problem, we've seen one of the very first examples we did is this transform pair that e to the power minus absolute value of t is the CTFT transform of it is 2 divided by 1 plus omega square. Now I claimed that the corresponding dual pair is the following. You can see here that you also have e minus absolute value of omega, but there's the factor 2 pi if you remember, because in the inverse transform you also have that factor. So my question here is to prove this. And you have to prove it directly.